All right, I believe the recording has started. Yeah.
Perfect. Let's try to keep them in time. So welcome everybody to these sessions of Reliability and Safety 3. I am chairing this session. I'm Antonio Filieri with Imperial College London and Amazon Web Services. And we will go through all the talks. We have 5 talks of 5 minutes each. I invite anybody who has questions to keep them for the end or just drop them in the chat. We will go through all of them during the discussion phase after the presentation. And without further ado, just to fit the time, I would invite Changling Liu from Case Western Reserve University to present your paper.
Hello, everyone. So nice to meet you all. Also, I'm going to share my screen. I'm Chang Liu from Case Western Reserve University, and here's our project, the PROMO, Precise Window Transition Graphs for Android via synergy of program analysis and machine learning. So first, let me give you some backgrounds about the window transition graph. So a window transition graph is a graph model for the apps GUI. So the nodes are the windows. Windows includes activities, dialogues, or menus, and the edges in this kind of graph are transitions among the windows, like these edges you can find in the example here. So the edges represent transitions, and transitions are caused by the events. Events are the tuples of widget and actions. Widget like the buttons, and actions like you clicking them. So intuitively, you can interpret this kind of edge graphs like if you click a widget on window A, it will jump to window B. So there exist existing methods for building this kind of window transition graph. The static analysis tools analyzes the source code and also look at the Android layout files to extract these kind of graphs. This kind of tools are comprehensive, but the limitation is they have very high false positive rate because of the inaccuracy and overall approximation made by these tools. Another track of tools are the dynamic analysis tools. They will actually run the app and generate a sequence of events to trigger the transitions among the windows. The graph generated by these kind of tools are always accurate, but it has very low coverage. As you can imagine, it's time-consuming to generate a comprehensive test suites and run all of them and reach every corner of the app. So here's our solution. We try to combine the positive sides of both the static analysis and the dynamic analysis, and introduce a machine learning model to resolve the uncertainty. Here's the workflow. For a given Android app, we will perform both static analysis and dynamic analysis to obtain a static WTG and a dynamic WTG. So we will use the dynamic WTG to verify each of the edges in the static WTG. If an edge is present in both of them, they are called verified and will be included in the final WTG. For those that can be only find in the static WTG, we can't tell now if they are valid or not. So instead of throwing them away or just use all of them, we feed them into a transition predictor, which is a neural network model. The model is trained on a large app dataset. So the model will give us a prediction of whether we should include this edge or not. So after all the steps, we combine the dynamic WTG and the predict edges, and we'll have a accurate WTG. So here is the detail of the machine learning model. It's composed of 3 modules. First is a widget embedding module, and the second is a window embedding module, and the last is a link predictor. So the embedding models for the embedding models, we feed in the screenshots of the window, source window, target window, and the widget, also the text and the GUI layout as a tree structure, and we unroll it into a sequence. And we use subsequent machine learning models like the CNN, DenseNet, and the LSTM to obtain vector embedding of the window or the widget. Next, we will feed these embeddings into this neural tensor network to predict whether there should be a link between them or not. So we did our evaluation on a data set of 40 apps, and 35 of them are from Google Play and 5 of them are from F-Droid. To guarantee the complexity of these apps, we just check them to make sure they have at least 3 windows and enough lines of codes. So we partition all these 40 apps into 8 groups according to the edge density, as a way to discriminate them of their complexities. Edge density is defined by the number of edges divided by the number of nodes. So well, we evaluate our workflow on this data set and find we have a precision of 90% and a recall of almost 80%. So at this point, we can say that Promo is highly effective in identifying feasible edges and in building WTGs. So that's all I want to share with you. Oh, okay.
We are going. So thanks, Chengling. There is some delay on my side. We're going through all the talks as I mentioned at the beginning. So I would invite Jianan Wang from Purdue University to present the second paper.
Yeah. Yeah. Screen now. So hello everyone. My name is Jianan Wang. Today I will present our work, Eagle, creating equivalent graphs to deep learning systems have been widely deployed in applications such as self-driving cars, machine learning, and cancer detection. As a result, the reliability of deep learning systems are of vital importance. However, it remains a challenge to test deep learning systems, as often complex, and it's hard to know the expected results. Let's focus on using differential testing to solve this challenge. The idea is input to different implementations of the same functionality. Given a bunch of input, we feed them to 2 different implementations of, and even compare the outputs of the 2 implementations to check whether there are inconsistencies. Here is represent potential bugs in the implementations. To utilize differential testing method to test existing techniques, test a pair of deep learning libraries to cross-check 2 implementations of the same functionality. However, there are 2 limitations. First, at least 2 implementations in which is unavailable for many different software functionalities. For many functions that only exist in one library, existing techniques cannot test them. Second, they require a high-level library such to switch across deep learning libraries. High-level library is hard to develop and maintain for different deep learning libraries. To address this challenge, we propose Eagle, which uses equivalent graphs, a single implementation. Now, let me introduce a motivating example of using Eagle to detect a real bug in TensorFlow. In deep learning, neural network functions, or RNN functions, can often accept 2 inputs. A common format is the first dimension represents batch size, and the second time steps. This format is called batch major. It is the usual input format developers use. The other format, time major, is time step and batch size in the second dimension. The time major format better fits RNN computation because RNNs compute batches step by step. For example, given 2 instances of 3-word input, I like dogs and I eat apples, the input can be fed to RNN in batch major format, I like dogs, I eat apples, or time major format, I like it, dogs, apples. Inspired by these 2 input formats, we can build a pair of equivalent graphs. Suppose initially time major input. We
function
with time major parameter set to true.
we can first transpose it to batch measure format.
Then
The bidirectional RN function
with time major parameter set to, and at last transpose its output back to time major. These two outputs should be equivalent. However, if there's a bug in for handling one of the graphs, we may detect incompatibility. In our experiment, we apply Eagle to test 13 RNN functions in TensorFlow and PyTorch. Eagle detects all bidirectional RNNs in TensorFlow incorrectly implement the time major. This bug is confirmed and fixed by TensorFlow developers. Here are our contributions. We designed 6 tools, which cover 6 categories of graph to test deep learning libraries. We propose a novel idea of using equivalent bugs in deep learning libraries and implement the idea as Eagle. We use Eagle on 5 of the latest versions of the 2 most popular deep learning libraries, TensorFlow and PyTorch. 25 bugs, including 13 previously unknown bugs. Thank you.
Shenxi Zhang from Fudan University. Will you please present your paper?
Okay, can you see it? Okay, hello everyone. I'm Chenxi Zhang from Fudan University in China. It's my great honor to be here to present our paper, Deep Tree Log, Trace Log Combined Microservice Anomaly Detection through Graph-Based Deep Learning. As we know, the microservice architecture has been the latest trend in building cloud-native applications. And in industrial, microservice systems usually have complex dependencies and changes frequently. So running in a highly uncertain and dynamic environment, microservice systems often fail due to various reasons. So the reliability is highly demanded in modern microservice systems, and how to comprehensively and precisely detect anomalies has brought about widespread attention. So trace and log have been widely used in anomaly detection for distributed systems. The existing work treat a trace as a sequence of service invocation, and treat a log as a sequence of log events. And most of them use deep learning methods to learn patterns from the normal execution and detect anomalies. Although there exist some approaches, they do not handle the problem of microservice anomaly detection well. First, we found that the current approaches only make use of trace or log, but in the microservice system, trace and log describe the different system behaviors. As shown in the figure, we can see this trace describes the service interactions for the request, and the log messages in each span describe the internal states and the behaviors of the invoked service instance. So the traces and logs can be combined for analyzing the runtime behaviors of microservice system. On the other hand, sequence-based representation cannot reflect the relationships between logs and traces. This is because asynchronous invocation and parallel invocation are widely used in microservice system. As shown in the figure, we can see that the sequence-based representation cannot reflect the crucial relationship between parent and children spans, and the temporal relationship between log events of the same spans. So the log events of different spans of a trace need to be combined in a way that the structure of the trace can be kept. To address the mentioned challenges, we propose the deep tree log. The core idea of the deep tree log is that first we parse the span of a trace into span events, which are a special kind of events that represent the start and the end of a service invocation. And then we use a unified graph representation to describe the structure of the trace together with the log events. And this is the overview of deep tree log. It includes 6 steps. First 2 steps are log parsing and trace parsing. In these steps, we parse log and trace into log event and span event. And then we use glue and TF-IDF to embed span events and log events into event vector. And we construct the trace event graph for each trace to represent the relationship between the span and the log events of the trace. And finally, we train a gated graph neural network-based deep SVDD model, which learn a latent representation for each graph and minimize the hypersphere that includes the representation of the graph in the training set. So in the online anomaly detection, the traces outside the hypersphere can be determined as anomalous. This slide shows an example of the trace event graph. We can see that the log events and the span events in the same span form a sequence by their time steps. And the events of different spans are connected by request and the response relationships. And to evaluate DeepTreeLog, we use the benchmark system TwinTicket. It is a medium-scale open-source microservice system and have been widely used. And we use photo injection to produce anomaly traces. As shown in the table, our dataset contains 14 fault cases of 4 fault types, and each fault case may include multiple fault instances in different services. And we have open sourced our dataset in the GitHub. You can find it in this website. And this table shows the effectiveness of DeepTreeLog and other baseline approaches. We can find that the DeepTreeLog achieve high precision and recall, outperforming the baseline approaches with an average increase of 0.37 in inference score. And we also evaluate the efficiency and the impact of some key parameters of DeepTreeLog. And more details of the evaluation can be found in our paper. Here is the end of our presentation. Thank you very much.
Where am I? Perfect. The next paper will be presented by Kylie Winston, University of Washington. Whenever you want.
Hi, can you see the screen okay?
Yes.
Okay, hello. Thank you, Antonio. So my name is Kaylin Winston, and today I'll be sharing our work on testing and repairing brain-computer interfaces. Every year, millions of people are affected by spinal cord injury, limb amputations, and stroke, all of these conditions resulting in motor and sensory impairments. Brain-computer interfaces, BCIs for short, offer a promising solution for these individuals, as they provide an interface for communication between the brain and hardware, and thus can be used to restore movement and sensation. Many BCIs first record signals from the user's brain, then use a neural decoding model to infer an individual's intended action from these recorded brain signals, and finally control a hardware device to perform the intended action. For example, a hand neuroprosthetic is a BCI that can restore hand movement. This BCI will continuously record signals from the user's brain, and when the user thinks of performing a certain task, such as making a fist with their left hand, the underlying neural decoding model will use the recorded brain signals to predict this intended posture, and then the BCI will control the posture of an external hardware device. Because such BCIs operate in highly safety-critical scenarios and in scenarios that require high precision, it is important that even the smallest mistakes or faults are eliminated. Current methods for BCI fault repair involve time-consuming recalibration sessions in which a clinician asks a user to either execute or imagine the same tasks that the BCI is expected to perform, such as holding various hand postures, while the brain signals are being recorded. The collected data can then be used for model retraining. However, this process may be ineffective at repairing faults because it does not prioritize the tasks for which the BCI currently performs work on. In our work, we explored how to effectively test and repair faulty BCIs by considering the underlying neural decoding model as software to be tested. We propose a human-in-the-loop methodology for testing faulty BCIs and repairing them by accounting for actual detected faults. First, BCI faults are automatically identified via expert-defined partial test oracles. These oracles can detect faults such as noise artifacts in the recorded brain signals, faults in which temporal validation faults such as invalid transitions between different output states, faults in which the output of the neural decoding model is inconsistent with the output of some auxiliary model, and faults based on domain knowledge. Secondly, once faults are detected, fault localization can be used to generate a fault-based task distribution. More specifically, we localize faults to tasks and input slices so that we can understand the co-occurrence of each fault with each task that the BCI can perform. And finally, this generated fault-based task distribution is used to guide data acquisition in a recalibration session, as now the clinician can focus on collecting data for tasks that co-occurred more frequently with BCI faults. The resulting training data that the model is then retrained on is thus more heavily weighted on the tasks that the BCI had a hard time performing well on. We evaluated this methodology on 5 BCI applications. These selected BCIs varied in their inputs, outputs, use cases, and neural decoding models, ranging from classical machine learning models to deep neural networks. By applying partial test oracles to test BCIs, we found that a non-trivial number of faults do occur, and that partial test oracles do detect faults that are indeed incorrect model predictions. We also found that faults localized to tasks and input slices. Finally, we found that retraining the neural decoding model on data collected using the fault-based task distribution lowered the fault frequency in some applications and does not impair the model performance. Our work demonstrates that an expert-in-the-loop methodology based on partial test oracles and fault localization is an effective way for testing and repairing BCIs. There are many avenues for future work, such as testing this on more realistic neural decoding models, exploring applying this methodology to other biomedical machine learning-based systems, and exploring how to test the programmatic system here itself. In conclusion, we're excited about the prospect of future research in the intersection of software testing and brain-computer interfaces, and we strongly believe that the application of software testing can increase safety and trust in BCIs. I'm extremely grateful to my co-authors for their collaboration on this work, the ICSU coordinators and chairs for organizing this event, and thank you for listening.
So our last speaker is Simanta Sa from University of California, Santa Barbara. Simanta, you can start whenever you're ready.
Can you see my screen?
Yes.
Hello everyone, I am Simanta Saha from Verification Lab at University of California, Santa Barbara. Today I'll be presenting our paper PREACH, a heuristic for probabilistic reachability analysis to identify hard-to-reach statements. This has been a joint work with Mara Downing, Dr. Tegan Brennan, and my PhD supervisor, Dr. Tevfik Bulton. PREACH is a technique that can identify if a target statement is hard to reach or easy to reach, given the program and the target statement. Let's consider this program from software verification competition benchmark. You can see there is an assertion statement. PREACH can answer questions like, is the assertion statement hard to reach for a random testing tool? Or to be more specific, PREACH can compute the likelihood of reaching the assertion statement if we run a random testing tool and the inputs are randomly generated. So PREACH does a probabilistic reachability analysis. Existing techniques that can be used for probabilistic reachability analysis are probabilistic symbolic execution and statistical symbolic execution. Now, the issues with symbolic execution-based techniques are there can be exponentially increasing number of paths in the program. As a result, linear increase in path constraint size can lead to exponential increase in cost of symbolic execution. The complexity can increase further if you are trying to use a model counting constraint solver for probabilistic analysis. Whereas symbolic execution-based technique deals with path constraint, PREACH needs to deal with only branch constraints. As a result, the exponential analysis cost can be reduced to polynomial time analysis cost. We develop a technique, Bridge, that trades off accuracy for scalability. Given the program and the target statement, Bridge first constructs a discrete time Markov chain model, and then, using a probabilistic model checking tool, it can compute the reachability probability. After that, given a threshold, Bridge identifies if the target statement in the program is easy to reach or hard to reach using the computed reachability probability. Bridge first extracts a control flow graph from the given program and also identifies the target assertion statement as a target node in the control flow graph. From the control flow graph, it constructs a discrete time Markov chain using dependency analysis, and we introduce a new concept called branch selectivity. For example, if you want to compute this probability in the discrete time Markov chain, how do you do that? For that, we use branch selectivity. First, it extracts the branch condition from the program. Then it constructs the branch constraints as an SMT leaf format. Then it makes a model counting query to the model counting constraint solver. And then using the domain size, it computes selectivity, or what we call is branch probability. Now, for example, here's a branch condition at line 2. For this, the selectivity is computed as 1 by 2 to the power 32. Now, computing branch selectivity based on only branch model counting is not enough, because it cannot actually catch variable updates. So we use abstract interpretation-based analysis for refining this branch condition and computing branch selectivity. Now, once we have this discrete time Markov chain using control flow graph, dependency analysis, and branch selectivity analysis, we convert this discrete time Markov chain to a DTMC model accepted by probabilistic model checker tool Prism. We also construct a PCTL query using the target node in the control flow graph. And we ask a query like, what is the probability that the target node in the DTMC is reached eventually? We have implemented this technique in a tool called Bridge, and there are 3 different versions of Bridge using branch model counting and different abstract interpretation analysis. We have evaluated our technique on software verification competition benchmarks, and we also performed some case studies. Bridge is available and one can run using the Docker file publicly available. We have assessed Bridge on software verification competition benchmark, and we achieve very high accuracy, precision, and recall. We have also compared to existing symbolic execution-based technique like probabilistic symbolic execution and statistical symbolic execution. To summarize the result, we see that Bridge can achieve better precision and accuracy compared to both probabilistic symbolic execution and statistical symbolic execution. Not only that, at the same time, it can also be faster. We see that from our evaluation result, Bridge is orders of magnitude faster compared to probabilistic symbolic execution and statistical symbolic execution. The technique we develop here, Bridge, can be used for different kind of analysis like probabilistic analysis of software, quantitative program analysis, or even guiding hybrid testing strategies. To end, I would like to say thank you to everyone. We present a technique called Bridge, which is a heuristic for probabilistic reachability analysis. And in this paper, we have shown that it can be used to identify hard to reach statements in the program, and it can be used in future for probabilistic analysis or quantitative program analysis. Thank you.
Takes a while for my camera to appear. So I would invite all the speakers to activate your video and audio. Thank you very much for your presentation. I never had to use my powers to stop you, so this was impressive. Great. So anybody in the audience who would like to ask questions, please feel free to turn on your video and ask, or turn on your audio, or drop them in the chat. We'll try our best to keep them within the time.
Yeah, so I have one question for the last paper, the theory. Yeah, so a very interesting paper. Yeah, so but I have a couple of questions. First is like, what's the motivation of computing the probability? Because like, if you can compute the probability, why not we just generate a test case and just cover it? So if you tell me this is a very difficult statement to cover, and I assume based on your introduction, you only can answer the question for the random testing, right? it cannot estimate the probability for other type of testing technique. So that's my first question. The second is like, yeah, so you mentioned about the probability. Then how do you measure your probability is correct? So how do you measure your precision, right? For example, you say 90%. How do I know it's 90%? I use the random testing to run 10 times and 9 times if cover it. So yeah, so sort of like there's something that confused me. Yeah.
Okay, so to answer your first question, that if we can handle other testing tools that are not generating inputs randomly. So in this paper, we have shown technique that you can compute the probability based on that the inputs are randomly distributed. But this is not a limitation. We just show a general technique. It can be extended to other testing techniques based on the probability distribution they have. For example,
Yeah, but for symbolic execution, you don't have probability distribution.
Sorry?
For symbolic execution, how do you get the probability distribution? Or like for other search-based technique, yeah.
Okay, let me give you an example. For example, in statistical symbolic execution, they use a user's profile, like which variables has what kind of probability distribution. So even in probabilistic symbolic execution or statistical symbolic execution, you can use different users profile for different variables, or you can use different distribution of the test input for that you are trying to compute the reachability probability. So it's possible. Here we show a general technique, but it can be extended to any kind of input distribution using a user's profile or weighted model counting. Does that answer your first question?
Not quite, but yeah, we can skip it then. So the second one is that why do you want to compute the probability? Why not just like, and because you spend a lot of effort and the result is just a probability. Why not we just do the testing?
Okay, so the point of doing that is that, so we are trying to compute a probability, right? But the main target is not to just only compute the probability. Using the probability, we try to answer questions like, is the assertion statement hard to reach or not? For example, if you are trying to use a random testing tool, for example, if you go to hybrid testing, they use fuzzing or a random testing tool with symbolic execution. Now, the problem they face is they do not know when this random testing tool or a fuzzing can get stuck, and you should take help from symbolic execution. So the technique we are trying to develop here can be used for a scenario where you are trying to assess the difficulty of this random testing based tool or a fuzzing tool. And then using this result that we are saying that this particular path in the program might be difficult for a random testing tool to explore, you should not use a random testing tool, but you can use the symbolic execution tool. So we are not using this technique just only for testing. It's just to identify some difficulty or assessing the usefulness of some testing technique or limitations of some testing techniques. And then using these results that we provide, you can also identify like what kind of testing technique that I should use here, or how should I take the help of symbolic execution based technique where it can compute exactly the path constraints and give you the input that should exercise that particular path. Does that answer your question?
Yeah, sure. Yeah, and how about like the last one, like what about the evaluation? How do I know
evaluation? Yes.
Yeah,
right.
Your probability is accurate.
Yeah, so in the present, in the paper, we actually show in terms of identifying hard to reach statements, and we compare with this symbolic execution based tool. But
yeah. How do I know it's 90% or 75?
Are you asking questions about the accuracy or?
No, because you measure precision record. So I want to know, like, for example, you say the probability for covering this statement is 90%, but in the real world, it may be 75%. How do you measure whether it's 75% or it's 90%?
Yeah, so to be practical, to answer the questions in a practical scenario, we are saying we are providing you a heuristic, and the computed probability might be exact in some scenario or might be close to the exact probability to some scenario. But what is shown in the experimental evaluation that it's very useful in identifying hard to reach statements. For example, if you go to probabilistic symbolic execution based technique, for programs where there is no like recursions or loops, and you can explore all the paths, probabilistic symbolic execution give you an exact probability of a particular path exploration. So also in the paper, we provide a table where we compare, like, let's say I'm using probabilistic symbolic execution, then what should be the probability? Then I'm using PH as a heuristic, and whatever the probability we are computing, we're trying to compare these two probabilities. Are those like the margin of error is like too high or is very close? So we provide these results in the paper. Maybe you can.
I reported in the chat, Tefik, with another author in the paper, I was mentioning that using probabilistic symbolic execution or a random testing tool as a baseline. I can jump in just for a second, not to abuse of my position here. It's I worked a little bit on the part on probabilistic symbolic execution. Usually, it's you can see the program as a kind of transformer of randomness. So the randomness is in the input. If you have a certain distribution of inputs, how this distribution of input is going to stimulate, let's say, to reach each of the branches in the program. So that's, in a sense, the kind of problem that probabilistic symbolic execution is doing there. The program is not normally probabilistic per se. It's the usage that make the behavior of the program probabilistic. Essentially, it transforms an input distribution into an output distribution or an observable distribution. That's the main application.
Yeah, I got your point.
So
So
I guess-
essentially, the evaluation is not to measure whether it's 90%. It's measure like whether
Exactly.
it's a hard to reach statement or not.
Exactly. So they, so from I read the paper, they start with the redefine like input distribution. They say this input distribution, according to probabilistic symbolic execution, is going to reach this branch 3% of the time, 5% of the time, 9% of the time. This is our oracle. How well can we approximate this result without, of course, incurring the cost of the symbolic execution?
Okay.
I also
you.
have some questions,
Thank you.
but I'll save them for later. First, anybody else from the audience?
Okay. I have a question about the paper deep travel. I hear some echoes.
Could be me. Let me mute myself.
Yeah, let's go. I have a question about the deep Trelog paper this for Chenxi, and I have read your paper. It's really interesting, and I have a question about your hyperparameter tuning about that mu value. Okay, and I found that it is kind of quite important in your training process. So how do you set the mu value if you don't know the real world distribution of the normal and abnormal traces? I mean, if the ratio of these two kind of traces are unknown, so how do you set the correct mu value?
Yeah. The mu value is in most situation we set it.
Like the question? I mean,
yeah. Using the mu in the deep path VDD. Yeah. Can you hear me? Hello.
I can hear you.
Yeah.
I mean, Shang Shu. Can you hear me?
Did you get my question? All right, I can repeat myself.
You mean the mu in the deep path VDD, right? The parameter. So I just say maybe.
I don't know if there is any audio issues. I think Shangshu was saying if you do not know the value of the mu parameter, how can you implement the approach?
Yeah. In our evaluation, we just set the mu as a low value. For example, the 1% or 3%. But in the actual system, we may have some valid data, and we can see we can determine the mu based on the valid data. And most of the anomaly detection approach assume that most of the training data are normal. So we can, if we don't have enough anomaly traces or anomaly data, we can just say set it the mu at a low value, such as 1% or 3%. I think it's the most things they do there.
Shangshu, please follow up.
Error or something. I didn't really. Sorry.
Sorry, it's okay.
Are you getting an audio issue, or it's a problem like with the...
Yeah, I may have an audio problem just now, so I'm back and I can see them. So did he just answer the question or something? Sorry.
Chenxi, can you repeat it in 30 seconds in the short version?
Okay. So in our evaluation, we just set the mu as 1% or 3%, And in the actual, in the industrial system or some real scenarios, we can use the valid data to set to find the optimal meal in the device VDD. And or we can just set it at lower values, for example, the 1% or 3%. It maybe get some well and some good performance in the evaluation. So yeah.
Yeah, I see the point, but if as in test data, you don't in the real world, you don't know whether a trace is normal or not, right?
Yeah.
So how do you, if you don't know that, but you have trained your system, you want to apply it on a real distributed system or just microservice systems, and how do you select the mu value during your training process to have the highest performance on the real data?
Yeah, but in the real data, we also have some a little anomaly traces in the historical data. We can set them as a valid data set, and to find some optimal mu in the loss function. Yeah.
So which means that you need to retrain your system periodically, and to adapt that system to your new data.
Yeah.
Okay, I see. Thank you.
It's a quick follow-up there from a big ignorant on deep learning. How expensive would be a retraining? Is there an opportunity to start from a pre-trained model and then to just, let's say, adjust it by feeding a small training set, or you will need to restart from scratch? Chenxi, sorry, I was asking in your case. So we were saying that we need to adjust the training. So do you need to repeat everything from scratch, or is there any kind of benefit in starting from a pre-trained model, and then hopefully, for example, some of the knowledge can be adjusted with a smaller training set?
Sorry, it's not clear.
So I'll try once more to see if it works.
Yeah.
So we have I was asking, like the retraining, when you want to use it use the method for another application, does it need to start from scratch, or is there any benefit in starting from a pre-trained model and then having like a shorter, for example, training session?
Yeah, but if you mean use the model in another application, yeah,
yes.
A new application.
Yeah, in a new application, yes.
Yeah, it must be train the model from hide.
Thanks. Next questions.
All right. Hi. Great talks, everyone. I actually have two questions for the author from Promo. So the first one is I actually looked through the paper, and I found that in table 3, the static analysis technique gators actually got recall 59-something%. Now your technique was able to improve that to 79, nearly 80%. Now my question is, if I understand correctly, you only verified the already generated edges. So how do you increase the recall if that's the case?
I'm sorry. What do you mean recall or increase the recall for what?
So recall and precision is like the trade-off, right? You increase recall, then you reduce precision, and the other way around. And based on the text, you say the static analysis usually have high recall because it overestimate, but the precision is low, which is shown in the table. Is precision low, recall is like 59%, I believe. But then your technique, if it's only verified, it should have smaller recall but better precision, right? Because it simply verified the edges that's already there. So how's it actually improve recall? As in, does it actually add more edges?
We do not only verify edges. Well, we have a machine learning model to predict unverified edges, and also we have a auxiliary, you can call that static analysis apart from just using Gator because we identify limitations from Gator by identifying transitions from dialogues to the other windows. So we have two parts of static analysis.
Oh, okay. So do you have any result for that particular static analysis? Because because your thing is based on that, it's be good to know like how much of the recall it had, right? Because it seemed to improve much more than Gator. So do you have any number for that off the top of your head, or?
I don't have the number for now.
Oh, okay. That's all right. Yeah, I just wondering because it is weird that the recall improved so much. And the second question is, it seemed that you actually compare your technique to the combinations of both Gator and Paladin, right? So the two component, and it seemed that the improvement is quite big. It's from like 53% to your technique, which is like nearly 90% precisions, and recall is also improved quite a lot. So my question is, does that mean the actual neural network, the NTN part of the techniques actually contribute quite a bit to the performance? I tried to look through the paper and I don't seem to have the actual performance for that particular part. Do you have any number on like if we just use the NTN, the neural network directly, what sort of number do we expect to have?
We have the end-to-end results. We actually measured the contribution of each part. I think the dynamic analysis contributed a lot, and the machine learning model also contributed. It's just as important as the dynamic part. Does that answer your question?
Yeah, no. I see. Like my question is, I'm wondering if you just use the neural network by itself, right?
Yeah. So probably I can.
Oh.
Yeah, I can. Yeah, if you directly use the neural network, I don't see it work well, because like you see the best synergy of our approaches is that we first have the static analysis, and then we have the dynamic analysis. So in fact, the dynamic analysis also find certain edges that do not exist in the static analysis. The reason is because the static analysis actually the model they have cannot accurately model the Android app on some apps. Not necessarily for some apps, the static analysis, if they are very accurate, you can see the whole picture, right? So that as you imagine, the records will be 100%, right? But in reality, that's very difficult. Yeah. At edge, they have dialogue, and so it becomes very difficult for the static analysis to cover all. So we further the dynamic analysis because they are not limited by this cover limitation. They can find certain more edges than the static analysis. So if you do a union of them, then you actually get a much bigger picture. Yeah. But if you do a union, we also have the evaluation to compare. If you union the static analysis and the dynamic analysis, I think my voice is breaking, right? Yeah. Hello?
No, it's fine. I think.
No, we could hear you fine. Yeah.
Okay, yeah. So if you do the union of the dynamic analysis and the static analysis, you get a much bigger graph, but the precision is low, the recall is pretty high. And then we use the machine learning to help us filter out like the edges that have low confidences. Yeah. But if you directly would like to use the machine learning, then essentially you need to consider like for every widget in one window, there is a possibility that this widget can change it to every other window. Then it becomes like you need to, for example, if you have 10 windows, 10 widgets, then it becomes like 10, I think it's 10 to the power of 10, right? The combination. And then you run the prediction for every combination. And then the result will be pretty bad. So you need the dynamic analysis and static analysis to help you reduce the combination and also improve the selection. Yeah.
Yeah, that makes sense because you need the graph to filter it out. Yeah, because it just looked like the improvement is quite big after you because I can see from the combinations to the final thing.
Shusheng, I will stop you here. I will invite you to continue that offline because it's getting very detailed, so I want to take all the time.
Yeah, thank you though. Sorry.
No problem at all. Any questions from the audience? All right, one more than one actually. I wrote notes here. For Janan, I was wondering, like, how much redundancy did you find into publicly, like, common deep learning frameworks? Because you need some form of redundancy. You need to be able to create, in a sense, a semantically equivalent transformation. So either you rely on inverse functions, or you need multiple ways of doing things.
I'm sorry, I didn't quite get your redundancy question.
What is your feeling about how much redundancy is in PyTorch or in big, let's say, deep learning libraries with which you work to implement?
What kind of redundancy are you talking about?
For example, if you want to implement, like if you want to generate equivalent graphs, effectively you're using different combinations of APIs, which bring to the same result. So this means that either you have like inverse function, for example, you transpose twice and you get back to the initial result, or you're using, instead of the API multiply, you're using add many times, for example. So in a sense, this could be some form of redundancy in the APIs. So you can do the same thing using different sequence tools. Is there a lot of redundancy? Is just a little redundancy? We read on the books that not much.
So I think the approach we use is we first we in our approach we obtain an APIs for each of our rules. We have 16 relevant rules, and for each rule we will obtain a list of relevant APIs that can be applied. And well, for each rule there is no redundant APIs. Also, the list will be separate for different libraries, like for TensorFlow and PyTorch. Yeah, and then we will apply our rules to each APIs to generate a pair of equivalent graphs and then execute it to check whether there are inconsistencies. So actually, I'm not quite sure about the redundancy you mentioned, because it's not our focus in our experiment things.
No, absolutely, it's not part of the goals of what you want to experiment, but to write down the rules, you needed to inspect a lot of APIs to realize what is possible to do. So
yes.
It was more of a feeling there. Sorry.
Oh, let me try to see if I understand you. I have understood you correctly, Antonio. You're interpreting that I can do, for example, the calculation using one API. Let's say I can do the same computer use API 1. I can do this same computer use API 2. You consider this as redundancy, right? Built into the library. That's what you're asking.
Yeah.
The kind of how much redundancy.
Yes, that's correct. I mean, it's just from your experience, of course. So it's not something that you can easily measure. But I assume that to write the rules, you found that, for example, repeated addition is equivalent to multiplication. Just maybe it's a trivial example.
So, for example, Janai, in your example, you talk about batch measure and time measure. I think in Antonio's example, is this considered some fundamental duplication that you could do time measure and you can also do a batch measure? Imagine in the system you can only do one way, right? Then you might not be able to use this Eagle approach to find the bugs. So don't know if redundancy is the right word, but I see what you mean. Some level of whatever that is. So I think the question is that in your experience, right, how often do you see this level of different ways to do the same thing? How often do you see it? Does that make sense?
Yeah, it reminded me a little bit of some work from Gorla and Carsaniga that they were trying to find redundancies in the APIs to make automatic repair. So they say, well, if I get an error of the multiplication, so let's go with addition, for example. So that's where it came from. But it's just based on your experience. It's not an experiment of the paper.
So since all our rules, our 16 rules, aims to develop equivalent graphs, so all the rules can be regarded as some kind of redundant graphs. Also, we have a specific category called API redundancy, which checks the API redundancies. For example, the convolution 3D API can be implemented using 2D version. Actually, in our experiment, we implement the convolution 2D with the 3D versions. So that's one example of the API redundancy. And we have like 6 rules in that category. And well, so at least that's some redundancy we
Yeah,
discovered.
exactly. No, this is the type of redundancies I was imagining, yes.
Mhm.
I would imagine that the 2D could just call the 3D.
Yeah.
And but probably they don't do it since we see the bugs.
Yeah.
Sorry.
Very interesting question, right? Are there more computational redundancy in deep learning library versus non-deep learning libraries, for example? That might be something interesting. Like I feel the developers intentionally to have this redundant computation, either for cross-checking or sometimes they have a different version for efficiency. Like from a semantic point of view, they might be the same, but they want a different version that's optimized. This might be something unique for deep learning code because the performance is really important. But it's a good question. Like we haven't looked at this more quantitatively, but obviously this kind of duplicate or some level of redundancy help us build this tool to find bugs in their code. But it's really interesting to look at, hey, more systematically, how deep learning libraries might be different.
Looks like you have just about enough time for ICSI 2023. So if you start tomorrow. Thank you. Thanks, Lynn.
Thanks.
Kelly, I had also another question. Anybody from the audience has questions to jump in? Kelly, I have a curiosity in this case. So one part of the approach consists in asking the humans to perform some specific tasks, which are probably useful to discriminate errors, which are part of the essentially to be detected. So how reliable are humans in implementing tasks? Is one of the parts is input validation in a sense. So I assume humans are less accurate or more accurate than software test suites. How did you find it?
To clarify, you're asking like in the recalibration session, the humans performing the tasks? Okay. So the tasks that are being performed are everyday tasks that a user would be performing, a user of a BCI that would be performing. So for example, if it's like a hand prosthetic, the user would be holding certain hand postures, such as this, for example. And so I think that would be pretty accurate. I think that would be pretty accurate.
So that's very simple operations in which you can trust the accuracy of the user.
I think we can trust their, yeah. One issue would be that like the neural signals that are being, the brain signals that are being recorded while the person is performing the task could potentially be noisy, which could introduce certain errors. But the tasks that the users are performing, I think we can rely on the accuracy of those.
And well, again, this is ignorance on the neural interfaces. So say that I'm performing a task correctly, but I'm distracted or I'm thinking about different things. So that's probably my problem, jumping from one point to another. Mm-hmm. Is this something that may affect the recalibration, or you observe that actually it works pretty smoothly, so there's not an issue?
Yeah, so I think that could affect the neural signals or the brain signals that are collected. I think that was one of the faults that we did actually explore, which is if the user's performing a certain task and they are, for example, blinking their eyes or distracted by something else, that could cause artifacts in the brain signals that are recorded. And so that, I guess, potentially may affect the recalibration. One of our goals was to be able to identify those faults during real-time usage of the BCI. And I do have my co-authors here, so they can jump in if they have any.
It's a pretty fascinating topic, asking mostly for curiosity, I have to say. We have 2 minutes for one last question. Everybody is shy. Okay, Samantha, I can use one for you, which is so the new framework relies in a sense on abstract interpretation. And what type of limitations of abstract interpretation you may inherit? For example, interprocedural operations or precision.
Right. So the main issue we find when we are developing Bridge, so we are using an existing abstract interpretation technique like Jana, which is for Java, but we see that it has limitation, like it cannot handle when you have some recursive calls to a functions, and then you need to model that into the Markov chain. So these are like certain types of limitations that we found, like you were trying to do interprocedural analysis, or you were trying to handle a recursive function. Then we see that the result we get from the abstract interpretation side is not so accurate, or sometimes it cannot handle certain situations. So as a result, these are also the limitations of breach from the abstract interpretation analysis side.
There's no free lunch anywhere, I guess. Perfect. I will use the last minute